Hello everyone. This side Dr. Nitin Sharma, Associate Professor, Department of Information Technology from Akgec Engineering College. And today I am going to discuss about the topic is B-tree. This topic is in second unit in DA, Design Analysis and Algorithm subject. Okay. So before discuss about the B-tree, we discuss about why we use a B-tree, what is the need of B-tree, right? So before understanding what are the features and what are the implementation process, what are the insertion process and deletion process of B-tree, initially I discuss about the B-tree, why we need a B-tree. Okay, so I'll discuss little about some theoretical aspect. Okay, so in front of you, you can see there is a form of a disk, which is basically a physical structure in your computer hardware. Okay, and this structure is, you can check, it is basically having a two things. First one is a sector. So this one is in triangle shape. You can see these are called sector, like sector A, sector B, sector C. Okay, and the circle form and the small circle form like this one, this one, this one. These are called track. And the intersection of this is basically called the block. Like I'm talking about this one. So this is basically a block, right? And what is the address of this block? Block is basically the union of sector and track. Okay, so suppose B, C, D. So this sector is suppose D, and this track I can consider is track 0, track 1. So this is track 1. So sector D and track 1. So the address of this block is this one, the union of sector and the track, right? So what basically data is stored in a disk into a block form. Okay, and what is the size of that block? The size of block is totally dependent upon the manufacturer. There are so many manufacturers, they are developing, they are basically producing the that hard disk. So they can just take the size depend on their manufacturer architecture. So suppose I'll just take in some example. So suppose the block size is, we can consider here 512 byte. Okay, or we can say that a bits. Okay, not byte, bits. We can take a small unit here. So the size of the block is 512 bit. Okay, so that block is stored in a form is like 512 bit. Okay, so I'll take an example. So you can see this is the example of that hard disk. So that hard disk is basically having some, you can see in a rotation form, and there are some sectors which is divided here like this, and there are some tracks. Okay, and this is the point. This is the head which is basically used to read the data from that hard disk. So what will happen basically, whenever this circle is running, so this head is moving around there like this one. So this circle is running like this, and this head is moving like this. So circle is moving in a place, but head is moving like this, like this, like this. So it is basically covering all the sector and all the tracks at a time. And if you read any data, so you must be know about what is the block address of that particular data. You can read it. Okay, I'll take some example. Suppose I'll take this one. Okay, so this one is basically a hard disk. Okay, so whatever data is required, it is basically stored into a hard disk. So this is my hard disk. Okay, and one more thing you must be knowing about is that is RAM. Okay, so whenever you need any data, you can access the data from this hard disk and get into the RAM and do the manipulations, whatever you want to do. Like either you can read, write, manipulation, and whatever the program you can run in the RAM. Once the program is executed, and again you want to store that data into the hard disk. So once it get the data from the hard disk, it do the manipulations and store into the hard disk again. Okay, so data is basically in two places. First is like in a hard disk, and second place is in a RAM. Okay, so like in the volatile and non-volatile concept. Okay, so if you want to structured or store or manage the data in RAM, you use the data structure. So data structure is basically used to manage the data into the RAM, right? Like we can use the linked list or array or whatever you can use the data structure, like a structure, union, whatever you want. Okay. But what is the thing you have to be used here in a hard disk? You have to store the data. So what are the structure you have to create it here? So here you can use the tree. Okay. Because most of the time, whenever you need to be access this data, you need to be just search and access the data only. You don't need to be manipulated. If you want to do some manipulation, you have to be read the data and into the RAM and do the manipulation, and again you have to store into the hard disk, right? So if you need to store the data into the tree, right? So into the hard disk, so you have to be stored into a tree format, right? So there are so many trees you can use to data store into the hard disk. So that data is stored into the hard disk in a DBMS. There are so many file systems. So database management system. So database management system is using the tree to store the data. Okay, got my point? So there are so many type of trees like in a data structure. So if you want to store data, you can use tree. Now I can understand. I'm trying to explain this DBMS, why we store data in tree format in the DBMS. We can take an example. Okay, I'll take an example. Suppose I have a table. Okay, so this is ID, this is name, and this we can say that age. Okay, there are 3 fields only. Okay, and suppose I'm having here 1, 2, 3, and so on, 100 records. So I'm having here 100 records, right? What basically ID is taking the memory. So I suppose that ID is taking a 2-bit, name is taking a 6 bit, and age is taking a 8. Okay, so total is 16. So it is taking a single row. If I'm talking about a single row, so single row want to store into the disk, so they need a 16-bit required into a disk. Understood my point? And initially you must be remember that the block size is 512. So a single block, how many rows they can stored here? So one block is taking a 16-bit and the block size is 512. So 512 divided by 16, 3, 32. So here you can see that total 32 blocks, 32 records can be stored into a one block. Okay, so one block can store 32 records. Got my point? So how many records I am having here? 100 records, right? So how many blocks we need? So we are having here 100 record. One block can store 32 blocks, 32 records. So if I can divide it, so here it is approximately 3.2 something, 3.2, 3.23 or whatever it is. Okay. So block never be used in a fractional form, obviously. So we need here 4 block, right? So we need to store these 100 record into the database. So we can write here 4 blocks. Okay. Now, if I want to access any data, for this table from the hard disk, how many blocks we need to be accessed at max? 4 block, because the data is stored into the 4 block. So maybe whatever element I am searching here, it is stored into the last point. So how many blocks we can be accessed here? 4 block. Got my point? So this is final. Now, what we do next? We do the indexing. What I am doing here? I am doing here indexing here. And in this table, I am storing only 2 elements. First one is ID. Okay. And second one is pointer. Okay. So what if basically they are doing 1, 2, 3 until 100, and one record is pointing out this address, second one is pointing out this row address, third one is pointing out on this address. Got my point? So this is the way the store data into another table, which is basically having the ID and the pointer. Pointer is basically point out that particular record. Got my point? Again, I am going to calculation for this one. Okay, how many blocks we need to store this data? Okay, so ID, I know that the size of ID is 2, and pointer I can take here 6. Okay, so ID is basically 2, or pointer we can take here 6. So total 8. So one record can take 8 bit to store. Okay, so how many block we need? So the block size is 512 divided by 8 is equal to 64 records. Got my point? So a block can store 64 records. And how many records I am having here? I am having here 100 records. So 100 divided by 64, which is something 1.8 something. Got my point? 1.8 is, we can just assume that 2. So we need here 2 blocks. Got my point? 2 blocks we need to be store this data. Okay. Now you can see the how many block you are going to be access here when I am doing a multi-level indexing, right? I am doing an indexing at one level. Okay. So what I am doing here? Here that data is stored into a 2 block, right? So how many block you can access at a time? At max 2 block, because this data is stored into the 2 block, right? So you can access 2 block at max whenever you are accessing this idea, this table. Okay, so suppose you want to be access any record, you can access first this table. So you access basically 2 blocks till now. Got my point? Suppose here you can see this, suppose this data is in block 1, this data in block 2, this data in block 3, this data is block 4. This is basically data stored in the 4 block, and you are going to be access this record, 100 record, okay, 100 ID record. Okay, so when you are accessing this table, you are going to access 2 blocks, but when this address is pointing out this one, so this address is stored into a 4th block. So no need to be access these 3 blocks here. You can directly access this 4th block. Okay. So how many block are accessed there? You can access only 1 block. So total number of block access is 3. Got my point? So when we are accessing this table only, when I don't have this indexing table, so we need to be access 4 blocks. Got my point? When we do the single level indexing, so how many blocks we need to be accessed here? 3. Got my point? So this is the way you can do another level of indexing. So when you are having a 1000 and 2000 records, so you can try to understand when you are having a single table, so you can access a more number of blocks. When you are having a multi-level indexing, you need to be access a minimum number of blocks. So when you are going to access a minimum number of blocks, so your accessing time is going to be large, minimum. Got my point? So that's why we need a B tree. What B tree basically do? What basically B tree do? B tree is basically inserting the element, okay, and I am just defining a range here. When this node is having the maximum number of value, it is automatically break up and it's go to the middle element is go to upside and is divided into 2 childs. So it is basically bottom to top approach. Got my point? It is basically going to bottom to top approach. Okay, so it is automatically creating the indexing. Whenever the number of element is higher at that level, it is automatically break up and go to the upside. The mid element or the median element are go to the upside, and the child is going to be left and right side. Okay. Again, suppose there are maximum number of elements are here, it is automatically break up and it is go to upside. Again, child is here. Okay. Try to understand with my example. But before this, you have to be understand why we need a B tree. B tree is basically providing the facility of indexing, because the indexing is going to be doing the fast searching in a table. Okay. I'm not talking about a degree order. I'm talking about only the degree. Okay. So whenever you are having any example in your exam, so they are giving some degree. So suppose you are having some elements, okay, and they just told you that, okay, you have to be create a B tree for this degree. Okay. So you must be remember two things. First is the maximum key, and second one is the minimum key. Suppose the degree D is equal to 3. Suppose the degree D is equal to 3. So the maximum number of keys are 6 minus 1, that means 7. D is 3. So the maximum number at on any node, the maximum number of key values are 7, and the minimum number of key elements are D minus 1, 2. So whenever I am going to insert and the node is having a more than 7 key, it is automatically break. For example, I'll take an example. I'll take here 1, 2, 3, 4, 5, 6, and 7. No problem yet. No problem. But if I am going to insert 8 here, 8 here, so it is basically violate the condition of that maximum key. What we have to do? So here I am having a 8 element. So we have to be write here 8 divided by 2, the upper values. Okay. That is 4. So the fourth number of element is going to be the upside. So like 4 is going to become a parent, and the left is having a 1, 2, 3, and right is having a 5, 6, 7, 8. Okay, so you can understand this is a bottom to top approach. The item is inserting at the bottom, and it is automatically break when the maximum number of key is greater than whatever 2 degree is given according to this. Got my point? Now, here we are having a 2 operations. First is insertion. Second one is deletion. First one is insertion, second one is deletion. Okay. So when you are inserting an element, whenever you are inserting element, you must be focused on that is maximum key. Because no need for minimum key. Minimum key is basically followed, but it is not followed for the root level. Okay. So whenever you are inserting an element into a node, right, that node is basically having a maximum key, it should be break. So you have to remember that condition, right? So whenever you are doing an insertion, you have to be focused on max keys. Any node in B tree never have a maximum number of keys. Got my point? Second, deletion. Whenever you are going to be delete any element, you must be remember that no node having the minimum key of element, less than minimum key of element. Suppose any node, suppose there is a node which is having a 2 element, suppose, okay, and if you delete this one and the condition is minimum key must be 2, so it is having 1, so condition is false. So never do this. So whenever you are going to be deletion, you must be focused about the minimum key. Why minimum? Because whenever you are going to be delete, it never go to the max condition. Na? If any node is having a 7 element, if you delete one, it is going to be 6, never going to be 8. Got my point? So there are 2 type of operations here, insertion and deletion. In a B tree, we discuss about what basically having this insertion and deletion. So whenever I am going to be doing an insertion, it is basically focus on max key. And whenever I am focusing on a deletion, we are focusing on the minimum number of keys. Okay. So this is a bottom to top approach. So again, I am just repeating little bit things. So B tree, this is a kind of hard disk which is having some sectors, some tracks, and the union, the intersections of this called block. The intersection of track and section is block, and the block address is basically the intersection of track number and sector number. Organized data on disk is organized that can be easily utilized by DBMS. As I told you that whenever data is stored into the hard disk, if you want to doing some manipulations, you have to be read and stored into the RAM, and after that you can just do the manipulation and again stored into the hard disk. When the data is stored into hard disk, you can use the database management system. So it is basically into the tree structure, right? This is a circle form, and I'll take an example like this is the table. So whenever the single table is there is 100 record, and the block size I am assuming here 512. Again, I told you that block size is 512 is assuming. It is totally depend upon the manufacturer. Okay. And this is also some assuming that this is taking this much of byte, this much of byte, this much of bit. So total 16. So whenever I'm accessing this one, we need a 4 block. When I'm doing the multi-indexing, we need a 3 block only. And I'm doing this one. So maybe we need only the 1 block, 2 block. So maybe the number of blocks are decreasing when I'm doing the multi-indexing. So through this, the accessing is increasing. That's why we need a B tree. Okay. And in the B tree, whenever going to create a B tree, there is a given a degree. Degree is having like minimum key 2D minus 1 and the maximum key is D minus 1. I'll take an example for the D is equal to 3. So maximum key must be 7 and the minimum is 2. And there are two type of operations here, insertion and deletion. Insertion, when we are doing maximum key, we must be focused on, and when we are doing deletion, we are focusing on minimum key. Got my point? So in the next class, we are going to discuss about the insertion and deletion process in B tree. Thank you so much.